So welcome everyone. We're looking at the practice exam, problem 3. So this problem is concerning this hidden subgraph problem. So this is more commonly called the subgraph isomorphism problem. So that's what I'm going to talk about it as. So I'm sure you've heard of the graph isomorphism problem before. It just says, given two graphs, could we change the labels of the vertices so that they become the same graph? So in a sense, if you took all the labels away, are they the same graph? And that's the question in general for graph isomorphism. Here we're looking at subgraph isomorphism, which just says, is one graph isomorphic to a subgraph of another? So they might not be the same graph, but they're essentially the same. At least a piece of one of the graphs is the same as the other graph. And we want to show this problem is NP-hard. So part A, we want to figure out a specific problem we should reduce from, and then we're going to describe our reduction. So the problem that I suggest we use is clique, because it'll have a very nice structure that'll be helpful. And the reason why this reduction implies it's NP-hard is, well, clique's NP-hard, and we're going to give a reduction from clique to subgraph isomorphism. So by transitivity of mapping reductions, this implies that our problem, subgraph isomorphism, is also NP-hard. So we have our clique problem, and we want to reduce it in polytime to subgraph isomorphism. So the input to the clique problem, we're given a graph G and some number L, and we're going to output an instance of subgraph isomorphism with the same graph G, and our graph that we're looking at to be a subgraph will be KL. So K is the complete graph on L vertices. So it doesn't really matter how we label its nodes, but one simple way we could do it is something like this. It really doesn't matter because all possible edges are there. So actually any permutation or any changing of the labels to KL will still be KL. So if we have any relabeling, pi of KL will still be KL. So it really doesn't matter how we choose to name the labels. So we'll just leave that arbitrary. And this will be our reduction. Clearly it's polynomial time. We output G, and then we output KL, and because L can be at most, the size of G, this KL will always be small. If L happens to be much larger than G, well, obviously G can't have an instance, it can't have a clique of that size, so we could simply just output no in that case. But for the general case, assuming L is at most n, this will be our reduction. So now we have to prove it's correct. So we want G to have a clique of size L if and only if G has a subgraph isomorphic isomorphic to KL. So that's what we need to prove. Now we could actually prove this as a biconditional because it's really easy, but let's just take it into pieces. So let's say G has a clique of size L. So let's say S is the vertex set of the clique. Then, to get KL, we'll just do a mapping. We will define f of u. The new label of u will just be one of the labels in KL. So you can just pick any arbitrary function here. That would be a unique way to map the set S to the set of L. So this is 1, 2, up to L. So any such function will work. So just let F be any bijection from these two sets. We don't even have to define it. So let F be a bijection from S to L. And notice one must exist because the size of S is equal to L. So of course any two sets of the same size have a bijection between them. This is just a general fact. So we have this F, and this F is the isomorphism, or the relabeling. So in particular, the subgraph induced by S is isomorphic to KL. So this subgraph induced by S is isomorphic to KL, and F is the isomorphism. On the other hand, if G has a subgraph isomorphic to KL, again, let's just say that S is the vertices of that, so G of S is the subgraph. So it's isomorphic to KL, which means that it has all possible edge connections. So it has all edge connections because KL does. This is just a fact about isomorphisms. The edge structure is the same. And it has size L, because of course it has to have the same number of nodes to be isomorphic. Remember, isomorphism is just saying they're the same graph if we change the names of the vertices. So if they were both unlabeled, they would look like the same graph. So of course it has, all edge connections, and it has size L, so it's a clique of size L. And that completes the proof. So the proof's almost immediate because these two problems fit really nicely together. Subgraph isomorphism is just a more general version of clique. You can just immediately solve clique if we knew how to solve subgraph isomorphism. So the reduction's very, very simple.